Okay, so geometric series are a thing. What page? What? It is like addition. So that's what series should call up in your mind.
Yeah. Triangles.
So a series is the thing about addition. And do you guys remember what a geometric sequence is from like algebra land?
Isn't that basically like lines where you just like have like 2x plus 1 and add 2 each time?
No. Okay, so let me give you that then. So a geometric sequence, a sequence is just a list of numbers. Okay, so a series is a sum of numbers and a sequence is a list of numbers. So a geometric sequence is a list like this. Like 2, 4, 8, 16, 32, 64.
I definitely remember this.
I definitely remember this. And the next one would be 120. And kind of so forth, right? Yes?
Yes. So
Okay,
yes.
so
All the answers.
just for the sake of clarity, how are you getting from here to there?
You double it and then you double it by itself.
Double it, double it, double it.
Dude, there's like a pattern.
There's like a pattern. Yeah, so a geometric sequence is one where you start with something.
Oh, and it has to be a consistent pattern.
So I'm going to start with something, like A1, just some number. And then I'm going to, from one thing to the next, I'm always going to multiply, and it's going to always be by the same thing.
Yeah.
So I'm going to call that thing R. Ooh. For rate, actually. So we're going to multiply by R. So here we're going to have A1R, and then we're going to have
A1R squared.
A1R squared, and then we're going to have A1R cubed, and then we're going to have A4, right?
Yeah.
No.
Oh.
Then we're going to have A1R to the fourth. Don't get creative. There's no creativity in this. Okay? They're always, you start with some number, and then between every step, right? Every time you move down in the list, you're just going to multiply by that R again. Okay. Yes?
But a geometric series.
And then a geometric series, right? So if you look at this and you think to yourself, series.
Then the R changes as time progresses.
No.
Oh.
Then instead of listing these things, you would
Ellipses.
add them together.
Whoa.
Which seems like a fundamentally terrible idea.
I don't know about that.
Use this in calculus.
A2, you know?
Nope, that's still A1, R3, and so on, right?
Use this in calculus.
Is this going to work? Like, is that going to stop?
Unless you
Why would
decide
it-
to stop it.
So there is such a thing as a finite geometric series, and there's such a thing as a geometric series, like regular version. Cool. So I'm not going to spend a ton of time talking about finite geometric sums, right, or series, because you can. I trust that you all can kind of add. Right. I'll give you a formula for how to figure them out if they're really long, but adding these is not particularly hard. The infinite ones are weird. Why is this weird?
It
Never stops.
It's like
You're
arbitrary.
considering
to add things
infinity.
that go on forever.
Yeah, right. It's a little strange to keep adding infinitely many things,
Yeah.
because what would you think that ought to come up as?
Infinity. There's no actual
Would
end.
Positive infinity.
probably think that comes out to positive or negative infinity, maybe.
Yeah. It's like the rate of, yeah.
But that's not actually always the case. This can come out to a finite value
If R is less than 1,
if R is less than 1.
that makes a lot of sense.
So here's a kind of silly example. Here's a 1 by 1 square. Okay, not this one. What R value have you seen? I'll do a different one.
I don't.
Okay, I happen to have 3 colors. So I'll do quarters. So I'm going to take my space here, I'm going to split it into 4 pieces, and I'm going to look at this sequence. I'm going to look at X, which I'm going to say is a quarter to start with. So I'm going to take one of the quarters and color it black. I'm going to take one of the quarters and color it green. I'm going to take one of the other quarters and color it blue. Then I'm going to take the other quarter and cut it into quarters. I would call it that quarter blue, or black, this quarter blue, and this quarter green.
Didn't you do this demonstration when you described why 0.999 infinite is equal to 1?
Yeah, I did.
Okay.
So this would be plus, what was a quarter of a quarter?
1/8.
No.
16.
16.
Okay, so your geometric sequence here then, right, is
64.
a quarter, a 16th,
64.
and then the next one's going to be a 64th,
And then 512.
and then 1/4 to the 4th.
Just do that.
Oops. And then kind of continuing, right? So what's S in the end?
1.
Since you guys have already seen this display.
Oh. 0. I remember this
If you
question.
if you use the argument that it's like the rest of it is going to be basically 1,
Wouldn't it be
But-
nice?
Okay, so
It gets infinitely small.
Could you, John?
no, it's
so the terms get really small, that's true, but the sum itself doesn't.
Can you solve using a triangle?
But it also.
Because it kind of looks like if you keep going in that direction, you'll end up with a triangle, but I don't know if it's necessarily true.
Nope. There's no way that'll be a triangle.
I'm just gonna keep coloring these until you guys figure it out. So
You get really
Okay,
close
yeah, I'm
to.
guessing that that means
Wait, what do you mean, what is S? S is the thing that all of the things sums, all of the,
S is not the thing that all of these add up to.
oh.
Because it's a quarter, and then it's a 16th,
So it's gonna add up.
and then it's a 64th, which means that it's,
Way less. I mean, it's like,
Well, it's gonna be greater than a 4.
yeah, it's gonna be greater than a 4.
3/8.
okay, it's definitely bigger than a 4th,
Yeah.
that's
Yeah.
good,
Barely.
barely.
Yeah,
Well, it's
seriously.
at least a 16th.
Well, it's at least a 16th bigger than a
That's
4th,
pretty significant.
which is, yeah. I mean, if this is a quarter and that's a 16th,
That's pretty significant.
it's like a quarter of a quarter somehow, right? Mind blown. Right? So, what I want you to see, right, is that this S thing, right, is the size of the black area up there.
Of all of the black.
Yeah, of all the black added together, right?
Right.
Because it's a quarter, that's this one, and a 16th, that's that one,
Looks like it's
and
a
a
third.
64th, that's this one.
It looks like it's 3rd.
It looks like it's a third.
Yeah.
Why does it look like it's a third?
Because you only have 3 colors and they all take up equal amount of space.
Yeah. Because the black area, right, and the green area and the blue area are the same.
Oh.
Yoga. Right?
Yeah.
Huh.
They're all the same area,
And they all add up together to get it.
and the 3 of them together exhaust that whole square, right?
Yeah.
Except for maybe the far upper right corner,
Mm-hmm.
which is just a point anyway.
Mm-hmm.
You can see that? But otherwise, they're all kind of assigned somewhere. So 3 things taking up 1 full unit, each of them must be
3rd.
a third. So your S here is a third. What about what?
Like, what exactly do the green and blue represent here?
They represent the area that I'm coloring green and the area that I'm coloring blue. And they happen to be the same as the black, right? Because a quarter is this green part, and a 16th is that green part, and a 64th is this green part. Basically, I'm just pairing them up, right? Well, not really pairing, but toppling them up. So these three are all a quarter. And then these three are all a 16th, and these three are all a 64th, and those three are all 1 over 4 to the 4th.
The geometric series is before 630.
Yeah, that seems a little weird, right?
So if you had.
You guys kind of with me? Like that got strange?
Yeah.
Okay, so you want to see a trick? It's related to this. I showed you guys the proof that 0.9 repeating is 1.
Yeah.
Okay, so let's do the same thing here. Because I think we really can just straight up do the same thing. Okay, so here's the thing. Right? I have a geometric, let me rewrite this. Okay, so I have a geometric series that sums to something. I'm calling it S. That's A1 plus A1R plus A1R squared. Really, I probably, let me standardize my notation a little bit. Let me just call this A, that might quite easier. Okay, so I have my first thing, and then I have R times that, and then I have R squared times that, and R cubed times that, and so on, right? Okay, I want to know what this sums to. So let me see if I can remember how to exploit the algebraic version of the, you guys remember that algebraic version of showing 0.9 is 1, 0.9 repeating is 1? How did I do that? Do you remember that trick?
I mean, you proved how.
I showed you with a picture, and then I also showed you with algebra. So the trick could be that you multiply by something and then add or subtract, right? So if you multiply this through by something, what would the obvious choice to multiply this whole business by be? Like if you were going to multiply a geometric sequence thing, right? Like geometric stuff. If you're going to multiply by something, what's the something going to be?
1 over A.
No. Yeah, close. The other thing.
1 over R.
What'd you multiply by all through here?
Oh. So
R, right? So I'm just going to multiply by R again. So I'm going to look at R times S.
Wait, why do you do that? What are we trying to do?
I'm trying to figure out what S is.
Okay.
Like, that's my goal. I'm going to try to figure out what this sums to in general.
So why do you multiply R by? Oh, because S.
I'm basically out of ideas, and geometric sequences and series have lots of this multiply by R, so I'm just going to try it.
Okay.
So if I multiply by R, what do I get?
AR.
I get A times R, right? Like, take this stuff, multiply by R. So you got AR, that's like this thing, right?
Yeah.
And then AR times R is
Squared.
AR squared. You guys see what's going to happen here? And in multiplying by R, I'm just kind of shifting everything down a space, right?
Yeah. So multiplying by R didn't really change anything.
It did change one thing.
The first is.
When I multiplied by R, the A went away.
Yeah.
You guys see that? So if I take and subtract that whole business,
You get A.
these guys are going to cancel, right?
Yeah.
These guys
Yeah.
also cancel.
Yeah. I see.
These
Infinite
guys
cancel.
also cancel.
Yeah. So you leave A.
All that cancels.
Yeah.
I like how you missed the ellipses. No, it's okay. Leave it. Leave it. Leave it. Leave it.
Okay, so I got that S minus R times S has to be A. Ooh. But I wanted to know what S is, right?
So just divide by R.
Close.
Or S.
Add R.
Oh, add.
So first here you should add, right? Which means that you really need to factor that S out of there.
Yeah, factor the S out.
Oh, well.
So if you factor, or if you think you have one S and somebody takes R of them away, how many S's you got? I think you got 1 minus r times s equals a. So s is a over 1 minus r.
Wow, S equals A over 1 minus R.
You guys with this? Okay, so there's one kind of caveat that I should add to this, which is this only makes sense if r is
Not 1.
Not one.
not
So
1.
less than 1.
But
Definitely.
But if R was 1, it wouldn't really be a geometric. It would be just the same number over and over and over.
Yeah, so keep in mind the same number over and over and over again is a geometric sequence.
Because you're multiplying by
And so
1.
adding the same number over and over again is a geometric series, but it doesn't come to s's a over 1 minus 0, or sorry, 1 minus 1, right? Because that's not defined anyway. So this formula works as long as, r is smaller than 1 in absolute value.
Okay.
So no,
It'll even work for negative r's as long as they're
Oh.
not too big.
um,
You guys cool with that? Don't let them be negative 1 or 1. That will get confusing fast. Cool? Okay. So, takeaway message. This thing has that sum so long as absolute value of r is less than 1. Cool? You want to see the finite version?